My research is really on integrating management flows with payments, and this is part of my presentation, or this is part of my research, this topic, so how we can use project bank accounts, how we can create a conceptual framework of a project bank account blockchain payment application for construction. So I'll first talk about what PBA is, and then I'll talk about how we can use blockchain for it. So PBA is a payment strategy that was first published in 2012 by the UK government. And how it works is, so payments from the client to the project are made through a PBA instead of to the main contractor. So the client makes payments to the PBA, and then the PBA makes payments to the rest of the supply chain. So the payment terms from anywhere in the supply chain from the client is a maximum of 30 days. So that's 7 days from assessment and 23 days from the completion certificate. And how this differs from existing payment systems is that as payments cascade down the supply chain, it can take usually up to 30 days or even longer in most cases for the payments to be processed between each supply chain participant. So for example, in a 6-tier supply chain, you can have up to 180 days payment terms from the bottom level supply chain to the top. So of course, PBA does have a lot of problems though, in that one, our payments are very complicated to manage with it. 2, it's expensive to set up with banks. 3, it does not stop the client from unfairly withholding payments. And 4, it reduces the main contractor's power over the subcontractors. So it revokes the main contractor's ability to withhold payments, which obviously the main contractors don't like, but the rest of the industry do. Oops, sorry. Okay, so in this presentation, I'll provide a PBA decentralized application where I simulate the appointment of project participants, the management of the cash-in, cash-out schedule, and execution of payments through the application. I'll also push data from management software into the application, and I'll process all of that with smart contracts. So how it works essentially is I convert smart contracts into spreadsheets, and then I connect these spreadsheets together in a way that if you change information in one of them, it automatically updates the state of the other ones it's connected to. So this allows systems that are typically fragmented, it allows them to interoperate much easier. For example, like invoice data, work schedule data, approvals data, and payment data can all be integrated into one. So at a very high level, there's 2 types of smart contracts I use. One is a trigger, and one is a table. So the whole purpose of the trigger is it's simply just an endpoint for a user to interact with to store data in the table. Triggers store conditions in them. For example, here, the condition points to the user's address, so only this user can interact with this trigger. So conditions can only be set once in a smart contract. As soon as you set it, you have to either redeploy the smart contract or deploy more triggers to change the conditions. And it's also very important, this is the reason why we don't store the conditions in the smart contract table and have users interact directly with the table, because this table stores lots of spreadsheet information inside it, and it's very important that we don't redeploy this during the project, because if we do, then we lose the spreadsheet data stored within it and all the timestamps of that data and who it was entered by. So to avoid that, we use another smart contract, which is the trigger, and you have users interact with that to store data in the table. So in my framework, I deployed 10 smart contract tables and 30 triggers, and I interoperated all of them together. This is just a small sample of that, though, because I couldn't fit in all 40 smart contracts into this page. So how it works, so I'll start from the left. The client would interact with SE trigger 1. To store a list of the project validators in that project validators table. So SE trigger 2 and 3, they have a very interesting condition about them, because rather than pointing to a user directly, they point to the address field within the project validators table. So the benefits of this is that the client can insert or remove project participants without ever having to redeploy SE trigger 2 and 3. The contractor who's inserted into the project validators table, they would interact with SE trigger 2 to store a list of all of the subcontractors in the subcontractors table. And then the contractor would also interact with SE trigger 3 to store a list of all of the scheduled works of those subcontractors. The scheduled works table has a very interesting property to it, because it has something called pointer data. This pointer data acts similarly to like an autofill, where when the contractor inserts either the ID number or the address of the main contractor, or of the subcontractor, sorry, it automatically checks the subcontractor's table and pulls any data that's relevant about that subcontractor into the scheduled works table. So you don't have to keep typing in the same amount of data, and also stops you from having to process data multiple times. So the project manager would also interact with EC3 to verify the completion of the scheduled works, which then triggers a payment to the subcontractors. So this is the process flow of that. So I won't go through each step. I'll just go through the main ones. So with number 1, the client would appoint a project manager by interacting with a trigger. That trigger sends a transaction to the blockchain. The blockchain approves that, stores it in the table. Then an API from the front end picks up the data from the table, presents it in the front end, and notifies the project manager that they've been appointed in the project. And a very similar thing happens for appointing the other project participants. So 2, managing the cash-out schedule, cash-in and cash-out schedule. So the main contractor would insert the cash-in schedule a similar way, so they interact with the trigger. Trigger goes to the blockchain back into the table, and then the user interface picks up the data and notifies the client to approve the cash-in schedule. When they approve that, same process goes to the blockchain and back to the user interface, and then it notifies the main contractor that the cash-in has been approved. The same process happens for the cash-out, a very similar process. So number 3, when the client sends a cash-in payment to the PBA, it notifies project participants that the cash-in has been received. When the subcontractor completes works, they do it through the interface as well. So they send a transaction to a trigger, back to the blockchain, and then back into the user interface, which then notifies the main contractor and project managers to verify the completion of works, which triggers an automated payment. So these are some screenshots of the user interface of that. So on the left, the client would insert project participants simply by entering their address and clicking submit. After they do this, this sends it to a smart contract. That smart contract pulls data from other smart contracts it's connected to fill in the fields in the central table. When each project participant is entered, it gives them access to other parts of the application. So for example, on the right-hand side, at the bottom right, that's a trigger that the main contractor would use to insert scheduled works. When the main contractor clicks submit, an API pulls the data from an Excel spreadsheet to populate the fields, and it sends it to the table at the top right. The other person who has access to that table is the project manager, and they would interact with that table to verify the completion of works, and then when it's fully verified, it will send a transaction to that subcontractor. So the technology stack of this, at the very fundamental level, at the protocol layer, we use the dev P2P protocol for the blockchain. libP2P is the protocol for any decentralized storage. TCP/IP, because it's a web application that goes through the internet. For the data layer, we store the smart contracts and transactions in the blockchain ledger. IPFS for contract documents, NoSQL for storing the front-end information, and any back-end information like APIs are stored there. For the back-end, Infura is the blockchain node that we use. Node.js hosts or processes any requests made from the front end, so any API calls, for example. AtraCloud Platform provided the user interface templates and smart contract templates. I was able to deploy my application entirely without having to write any code because of all of the templates provided by the AtraCloud platform. Any blockchain application requires an instance of Web3. Web3 allows things like MetaMask to connect your blockchain wallet to a web browser, and I use a standard front-end setup for deploying the web page. So the cost of everything. So, actually just the cost of the smart contracts. So each smart contract, I deployed 10 tables. The average cost of that was $5.40. I deployed 30 smart contract triggers. The average cost of that was $3.16 each smart contract. And I averaged maybe 500 transactions, might be correct for a project, might be less, might be more. But the average cost of that is 40 cents per transaction. So it's, to deploy the entire application, it's just under $350 US. But of course, these are just the smart contracts and transactions. So there's other costs that need to be considered, such as an enterprise user interface where you have like login portals and more security features. So that costs money to build. The testing and long-term management of the app is something that I haven't looked at, but any web page application that you host needs to be continually maintained. So the same with a blockchain application. A building of APIs. So I've built APIs to connect Excel spreadsheets to the user interface, and that's not so bad. But if you build APIs that connect like an ERP system to a front end, that can be very expensive. Auditing of the smart contract. So just because the smart contract works, it doesn't mean it's actually fit for use. For example, there might be lots of holes in it where hackers can exploit the coding of that. Insurance against faults in smart contracts. So blockchain hasn't been around for long enough for us to be able to correctly insure it, and who owns a smart contract, that's another question. And who's to blame? Is it the coders, or is it the people that deployed it, or just a lot of questions there. And also, how do you convert stable coins to fiat currency? So that's another problem, because even though we can have things like stable coins that peg national currencies at 1-to-1 ratio, these stable coins are still not legal tender technically, so you can't pay someone with a stable coin and they can't go into the shop and buy something with it with a stable coin. So there needs to be that conversion, and that can either be provided by someone like a DeFi protocol or banks, but banks don't really like to use blockchain very much, so either one of those two. So privacy on a public blockchain. So how do you achieve that? So in 1985, there was a paper published called The Knowledge Complexity of Interactive Proof Systems. The easiest way to explain this in the most typical way that this is explained is providing proof that you are over the age of 18 without you publicly revealing your date of birth. And you can have a mathematical proof that can provide that information is correct. In a more practical context, how you would use it is providing proof that two people transacted for an agreed sum for an agreed contract while obscuring the identities of the transacting parties or the transaction value. That's one more practical way to use it in construction. However, if you use zero-knowledge proofs, you have to deploy on a layer 2 scaling solution like ZK rollups. So I would have to redeploy my application on top of ZK rollups in order to use it. But there's a better way to achieve privacy where you don't have to use layer 2 and you can deploy it directly above the mainnet, which I'll talk about next. So in 2001, there was a paper published called How to Leak a Secret, and it talked about ring signatures, which was later used in blockchains as with stealth addresses. And so how this works, so each blockchain address can produce sub-addresses. These sub-addresses you keep completely private, and you don't tell anyone what these addresses are. So if you want to receive a private transaction from someone, you can use the stealth address to receive the payment. So you send that stealth address to the sender in like an invoice or something. But to increase the privacy even more, what you do is you encrypt that stealth address with the public key of the sender, so only they can decrypt it with their private key. So all you'll see in the blockchain is that the sender sent a transaction to a random public key every time. Nobody knows that that public key is owned by that recipient. Only the sender and the recipient do. If the sender also wants to be extremely private, they can produce their own stealth addresses. And of course, if the recipient wants to prove that they are the official owners of those addresses, they just create a public key signature and include that when they send the stealth address over. You can use an application like Umbra to manage these stealth addresses, so you don't have to actually do all the mathematical work to manage the stealth address protocol. You can outsource it to an app like Umbra completely. If you want to test out this application, you can click this link here. So it's open, it's running all the time. What I've done with the application too, so people that don't have blockchain wallets, I've put blockchain wallets on there. So on the page you can see there's multiple links to the addresses. So when you click the link, you can use a mobile application as well. So you just click the link, it logs you into the application with a blockchain wallet already. You won't have access to the private keys, but you don't need to because it automatically logs in the background. If you want to check out the coding of all of the smart contracts deployed, you can check it out on that GitHub address, where you can see the coding of all of the smart contracts. So that's my presentation, and thank you for listening.
Thank you very much.